This is going to be a brief overview of the docking workflow that I use to perform protein ligand docking in Rosetta. The instructions that I'm going to specify are going to be mostly specific to the directory organization that I have on my HPCC, but they can be generalized, and I also use certain Python scripts that manipulate files in these directories, and they're specific to the directories. But those can also be modified fairly easily to ignore the directories if you plan on doing everything in just one folder. Or you can just forego the Python scripts, and there's another tutorial. You can follow the standard Rosetta protein ligand docking tutorial given by the Myler lab. But this was intended to be higher throughput. That's why we made these scripts. To account for several protein structures and hundreds of ligands, whereas the Myler lab tutorial focuses just on one protein and one ligand, which is what I'm also going to mention here. So to begin, I just chose a protein. We can begin docking. This is a peroxidase, I believe. It's just a random protein I found on the RSCSB. And the ligand I'm just going to model the docking with is this small thing. Very small molecule, not a lot of rotational space, very basic. So prior to beginning the docking, you should have an idea of where the ligand binds, preferably. Although if you don't, there's also something called global docking, which you can do, where Rosetta will sample as much of the surface as possible. But that's more complicated, and we spent many months, Ray and I, 2 years ago, developing an algorithm to efficiently conduct global docking. And this was done with a server called CASP, which I'll briefly mention. And this server, you can upload a protein structure. In this case, I already uploaded the 4BLK structure. And this will output where possible binding pockets are based on geometry. So the red pocket is by far the largest, and there's also a small possible pocket here and one there. Our algorithm, to briefly summarize, looked at the largest pocket and the smaller ones only if they had volumes greater than 10% of the volume of the larger pocket, which these, simply through visualization, you can tell they do not meet that criterion. So if we were to use this CASP program, we would receive two files, namely I can actually show it here. CASP would output two files, namely a POC info file and a .sphere.json file. And we have a Python script that will look at these, and it's going to select the coordinates of, in this case, the largest binding pocket. And that is going to be fed to Rosetta, so Rosetta can initiate the docking in this largest binding pocket. But let's say that you don't want to perform global docking, you don't want to do CASP, you can just select a coordinate that you want to initiate the docking at using this very handy PyMol command. Excuse me. So I selected an atom there. And this will give you coordinates. And let's just select these coordinates. Let's save them in a text file. And I'm going to show you how to input them so you can tell Rosetta that you want to start the docking at that specific location. Let's just say that's our desired input. So in this directory structure, you upload the CASP results if you want to use them. They're needed by default, but you can just upload anything and modify them later if you don't want to use them. The ligand is needed. I have a bunch of ligands in here, but the one we're interested in is AD drug 1, and this is already in here. And the protein, 4BLK. So these are all the inputs you need initially, and you will generate some files using the first Python script that I'll mention. You'll generate a conformer file for the ligand, which will contain all of the rotational possibilities, because when you're docking, you want to account for the flexibility of the ligand. You'll get a params file, which will tell Rosetta how to deal with the ligand. You'll assign partial charges to its atomic positions, and you'll also get a concatenated file with the protein and ligand together. That's actually what Rosetta uses to perform the docking. So let's shift over to the terminal, and let's go to the okay, so this is the directory, docking scripts, where I keep all of the scripts that I use in the docking. And the first one that we'll be looking at, there's two that I'll discuss in this intro, is step one. There we go. Step one, file prep.py. So this is the one that's going to generate the params file, the conformers if you need them. I already had the conformers since I've already used this ligand in docking before, but it can generate them for you if you do not have them already, and the concatenated file. So let's just run that script. It's going to ask for the protein ID. This is just the name of the protein, the code, the RCSB code, because this is the input structure that we put in. As you can see, its name is just 4BLK, so that's what you input. If you named it something else, that would change. It's a monomeric protein with just one chain. That by default is going to be A. And are there new ligands? If you did not upload this ligand prior, your ligand prior, and generate conformers of it, you would say yes, and it would generate the job that will run the conformer generator on it. Since I've already done that, no is going to apply here. And now you can, it will create a job, and let's just look at this job very quickly. Step one. Okay, so what did it do? Here you can say it's generating a moles to params output. This by default generates for all the ligands that you have in your ligand directory. I only care about AD drug 1. These are other ligands I had in there from previous docking runs. I'm just going to delete them and run it just for AD drug 1. And if you scroll down, you can see that it also concatenates the files. So it will concatenate the protein file with the ligands. So let's just take care of that really quickly. I already have this file on my desktop, but that shouldn't change anything. Okay, so we only care about AD drug 1. Everything else can go away, so we can just delete it. Okay. Save it. Specifications are, these don't matter. You have one task here that says 5. That's more than sufficient. But for the actual docking job, I'll mention how you can optimize those. Okay. Let's upload this back. Okay, so now we can actually run that command. Okay, and it should take, for this, I would say maybe 20 seconds at most. Oh, already done. Great. Okay, so this should have generated a params file, so we can go to intermediate files. This is where I store the params outputs. And we see that AD-drug1, the ligand of interest, has a params file. This will tell Rosetta how to process it. Also has a PDB file for the ligand, and this will be used to concatenate with the protein PDB structure. Now, concatenated files, they should be here. So you can see it was concatenated with all the other ones previously, but it's also concatenated with the one of interest here. So that all went well. And the conformer file was generated previously, but to show you what that would look like, being a small molecule, it's not going to be very flexible. There's not many rotatable bonds, but this is just an example of what a conformer file would look like. So each of these different iterations will be docked to account for the flexibility. Okay. That's all good. Now let's run the second Python script. And that would be step 2. This is the second one, and the last one you'll do before actually docking. Again, specify the protein ID. And the score function. By default, I use pre-Talaris 2013. There are other ones you can use, but this one's been proven to be the best for small molecules. So. Okay, so now, once this is done, this will generate a job that will actually submit the docking, but there's some things we should look at first, namely the XML file. And the XML file is what tells Rosetta exactly where to start the docking and the area that will be sampled during the docking. So let's just see what that looks like. Okay, so you can see here, these are the starting coordinates. These are not the ones we used. These were the ones based on the cast-P input, and I didn't actually bother to check if the atom that we selected in the beginning actually corresponded to the largest binding pocket identified by cast-P. I'm going to presume not, because the coordinates are very different, so I'm just going to change these to the ones mentioned. So you can just fill in the fields. If more than one possible binding pocket is selected by the algorithm we have in place, you're going to see more than one coordinate here. You can change them as you please. And it doesn't need to be this specific in terms of significant figures, but this is what Pymol gave me, so I'm just copying and pasting it. Okay. And another thing I like to change is the box size. And the box size is, it refers to the dimension of a cube in which the docking is performed. So 14, this is angstroms. The ligand will move around in a cube of 14 angstroms with centered at this starting coordinate. So if you want to sample a larger space, you can change this. I usually change it to 17 or 20. And the scoring grid refers to all of the residues that Rosetta will analyze in the interaction. Again, this is the dimension of a cube that will contain all said residues. So 30 is probably fine for this small ligand, but usually I change it to 40. So let's just save this file and upload to replace this one. Perfect. And one last file we need to examine before actually running the docking is the options file. This will tell Rosetta where it can find all of the other files needed for the docking. So it's a mess because I haven't deleted any of the ones here, but let's look for the relevant options file. Should be towards the bottom. It's going to be AD-drug1. There we go. Okay, let's download this file. And let's look at what it tells us. Perfect. Okay, so this will tell Rosetta where it can find the concatenated protein ligand file, and this is in the concatenated files directory. This will change. You'll have to change this if you're using a different directory structure. This was all based on a template that our Python script used. It will also tell it where it can find the params file for the ligand that we're interested in, and the XML file. So these are all named properly. I don't need to change these. But one thing I usually do change is the end struct. And this tells Rosetta how many outputs it will generate, how many docking iterations it will perform. So for each coordinate, I like to do 1,000. That's the suggested amount. It will conduct like 1,000 runs at that starting coordinate, 1,000 like translations, rotations, all of that. And if I have more than one coordinate, I'll scale this accordingly. So I'll do 2,000 for 2 and etc. This is fine. I only had one coordinate I was interested in. So I'm just going to save this file and re-upload it. Okay, and that's good to go. This, everything for docking is ready. We'll just have to manipulate the actual docking job. But before I do that, I will go to the outputs directory, because a directory has been created there where we will see the outputs. And this was created by the second Python script we ran. So all of the outputs in the docking will show up here. And then we're going to use a third Python script, which I won't get to because it will take too long to explain. But after the docking's finished, we essentially have all of the outputs. We're going to have 1,000 for this one, and that script is going to extract the top 10 results for the docking, or whatever top X results you want. So you can modify it accordingly. Let's go to the docking job. So the docking job should have been generated. There it is. Let's see what it tells us. Okay. So this by default generated, excuse me, a docking job for all the ligands in the directory. If you were only going to have one, you're only going to see one here. So I'm going to have to get rid of all the ones that it populated by default that are not AD drug 1. Okay. And now what you would do is optimize the computational parameters. So you only have one line, so the number of tasks that you're going to use is 1. CPUs per task, I found that the optimal number is around 13 to 14. If you have more than that, it's really diminishing returns in terms of computational speed. And with 13 CPUs, you're likely to actually be able to submit the job more quickly because jobs with far more resources can be delayed in the queue. Memory per CPU, I usually put 8 or 9. It's sufficient for these sorts of tasks. And let's upload this modified one. And the docking, just one of these dockings, given that it's 1,000 outputs, this would take about a day and a half to run, assuming it gets submitted in the queue within a couple of hours of you actually running the docking command. I don't know why it's not uploading, but whatever. It's okay. No, it's good. Okay. And to show you an example of outputs, for instance, this is a completed docking run. This one's probably going to take very long to load because there's over 3,000 files in here, if it will even load. If not, I'll just go into the summarized directory of it. Yeah, okay, I'll just see that one. Page has become unresponsive, but anyway, so once you have the full list of however many thousand outputs you're going to have, there's a third Python script called step3 dockingdocs.py that will go through that. It will find a score file. Rosetta will output a score file for the entire docking run, which will list the Rosetta Energy Unit scores for all of the docking outputs. And the lower that score is, the better it is. It's analogous to free energy. So it will find those and sort them based on the interface delta X scores, and it will There we go. Okay, loaded. So this is an example of a score file, and this is the best pose. Instead of doing the top 10, I just told it to select the top score for this one. And that is basically it. You can perform plotting, you can do interface analysis on the outputs. So it's going to be a score file. It's a mess, but the relevant metric is interface delta x. Right there. There we go, interface delta x. That's a pretty bad score, but the more negative, the better. And you can see that for this past result, you can see how it did the docking, what it will look like. Perfect. Okay, so you can see there's the ligand there in the center where it was docked. There we go. So that was the coordinate we selected, and it moved around, and it found this as the optimal position. So yeah, that's docking. The third script is you just run it, and you have to modify it to extract the top nth positions. But other than that, that is basically it. Thank you very much.